There we go. All right. So first of all, everyone, thank you for those who are attending. Thank you, Mr. Amber, Mr. Sudeep. Let me introduce you gentlemen first. Both of these gentlemen come from eBay. Sudeep is a staff engineer, is an expert in building scalable and resilient distributed systems that handle petabytes of unstructured data every day. He has industry experience spanning across domains such as e-commerce, embedded systems, and telecom. He is a primary author of papers published and reputed in international conferences and hold patents in distributed systems. Mr. Amber is the director of engineering for the Telemetry team in eBay. And with that, I'm stepping out. Gentlemen, you guys have the con. I'm going to keep an eye out. If anyone has any questions, please put them in chat and we'll try to address them. And again, thank you both, gentlemen. Over to you.
All right. Thanks, John. So my name is Amber. Sudeep and I are going to kind of tag team this talk today. We are here to talk about how we are building distributed tracing capabilities using ClickHouse at eBay. Next slide. So for folks who are not familiar, eBay is a global e-commerce leader with presence in about 190 markets. We have about 150 million active buyers on the site with 19.5 billion GMV. GMV stands for gross merchandise volume as of Q3 of this year, and about 2.5 billion in revenue again as of Q3 of this year. So these numbers are just to give you a sense of the scale that we kind of deal with in our systems. Right, next slide, Sudeep. So before we kind of go into the distributed tracings capabilities and the specifics, I'd like to give an overview of our observability platform, as part of which we are building the distributed tracing capability. So Sherlock.io is the name of the platform. It's a centralized observability platform for all of eBay. And this means that eBay's centralized operations team, SRE team, and all the engineering community at eBay uses this platform to monitor all the applications, the services, and the experiences and the platforms that we are building within eBay. The platform supports different telemetry signals like metrics, logs, events, and traces. And it's a highly scalable platform that deals with millions of data points per second for each one of these telemetry signals. Next slide. So going a little bit more into specifics of the platform or some more details of the platform. So this diagram or this chart or this slide basically gives a very high level overview of the platform. So going from left to right, the left box represents the eBay's technology stack. So going from bottom to top, we've got our data centers, we've got the compute, storage, and network layer deployed within the data center. Then we've got our cloud. We have an internal cloud deployed on top of that infrastructure. And then we've got databases and platform services deployed on top of the cloud, which power the applications and services and experiences that our engineers write for our customers. And then we've got business metrics or KPIs that are used to track the health of our business. Now, across this entire stack, we collect telemetry data, and that is shipped to our centralized platform, which is indicated by the box in the middle. So going into that central box, that's the Sherlock.io platform. And again, going from left to right, you'll see that the platform is kind of bookended by our gateway APIs. So on the ingestion side, we've got what are called ingress services, and on the consumption side, we have what are called egress services. So the idea behind these gateway services is to abstract the underlying persistence layer from our customers, right? So we have established contracts with our customers, from an ingestion as well as from a consumption standpoint, and then we adhere to those contracts, and we abstract away the persistence layer from them. Now, the middle box where it says advanced compute engine, that's kind of the heart of the platform, and we built various capabilities within that compute engine. So some of the examples are, like, for example, you see extract and transform, where we ingest data, transform it, into a format which is used for persisting into our storage layer, and then it's used for fast querying. We also have an enrichment capability where we've built a common taxonomy across all of our telemetry signals, and this enrichment capability is used to adhere to that taxonomy, which is then used for faster correlation, etc. We've got anomaly detection and alerting capabilities, which a lot of teams use to monitor their services and get notified if there's an anomaly that's detected. So these are kind of some of the capabilities that we built within the platform. There are many more, but these are just some examples. On the top, we've got a common kind of control plane, which is used to manage all of these components of the platform. At the bottom, like I was saying earlier, we have a persistence layer, which depending on the type of telemetry signal that we are ingesting, it goes into different data stores. So you'll hear about how we are using ClickHouse today for tracing for the tracing telemetry signal. We bring in external data in the form of we have a config management system that hosts or that has a lot of rich data set that we bring in again to adhere to that common taxonomy that I was talking about, but we bring in all of this data to enrich the telemetry signals. And then we have a common user experience in the form of Grafana. Again, as Sudeep kind of walks through the slides today, you'll see some examples of how we are using Grafana for tracing. There are a variety of use cases that this platform serves. We've got some auto remediation systems that utilize the signals from this platform to do auto remediation. You obviously have like dashboards and charts that are being plotted on time series data. There are some trend analysis that happen. So for example, an example would be, so our infrastructure capacity team looks at this data to forecast our infrastructure capacity needs for the upcoming years. We've got alerting. So this is the most common use case from an observability platform. And then we've got a few API customers who consume data from this platform for a variety of use cases. All right, Sudeep, next slide, please. All right, so we are here to talk about specifically about distributed tracing. So like I was mentioning earlier, tracing is one of the type of telemetry signals that comes into the platform. And for folks who are not familiar with what distributed tracing is, distributed tracing is used to track request flow, to track how a request flows through multiple applications. So an example would be if you're trying to buy something on eBay, right? So you search for an item, you view an item, you add that item to your cart, you add a payment method if you don't have one, and then you check out, right? So that entire request flow goes through multiple applications, and distributed tracing is a way to stitch that flow across all of these applications. The most common use cases for distributed tracing are to identify errors or bugs through this request flow, and to also identify if there are any performance issues within this flow. And the use case would be, so I know the 99th percentile latency for my service is high, but in what context was this? In what context is this high, right? And once I get an example of the context in which it was high, can I get some additional data in the form of events or logs to debug that further? Another use case that we see where distributed tracing is used is to map out service dependencies, right? So since the distributed tracing, this mechanism is used to track the request flow, it can easily be used to figure out, map out a service graph and figure out which services depend on each other. And distributed tracing kind of is in the middle of all of these telemetry signals. So you can go from traces, you can jump to metrics, you can jump to logs, you can jump to events. And again, Sudeep will show you an example of how we are doing that today. All right, Sudeep, next slide, please. So as we started building distributed tracing at eBay, we kind of started looking at in the open source to see what projects exist out there to deal with this problem. And we saw that Open Telemetry is one of the widely adopted projects with large convergence in the industry behind this project. It is CNCF backed, and it provides a bunch of agents and libraries to adopt easily. It also supports multiple languages, so that's a big plus. That's a big plus for this project. So we've kind of adopted open telemetry standards at eBay. And to talk about how we are doing this specifically at eBay, I'm going to hand over to Sudeep to take us through that.
Yeah, thanks, Amber. Hope I'm audible. So good afternoon, everyone. Myself, Sudeep. I'm a senior engineer in eBay and part of Amber's larger telemetry organization. And currently, I'm leading the distributed tracing initiative. Amber provided us a brief insight into our existing platform, reduced us to into tracing, what is the significance, also touched upon why we decided to embrace open telemetry. Now, my focus during the presentation would be to go a little deep into our current trace offering. I'll be talking about different components that we are using, how our deployment looks on Kubernetes, what kind of visualization experience is available for our users. At a very high level, the schema representation of the trace data, what are the different challenges that we are seeing in terms of adoption or in terms of even integration. So it is imperative that I talk about OpenTelemetry Collector first, and we use it extensively within our deployment. So essentially, it is a vendor agnostic implementation. It's implemented in Golang, which allows you to accept different kinds of trace formats, Zipkin, Agar, or OpenTelemetry's own protocol like OTLP or OTLP HTTP. Apart from that, you can customize a pipeline wherein you can add your custom processors. So as the data goes through your pipeline, you can massage the data, transform the data based on your needs, and then you can have things around rate limiting, sampling, and so forth. Finally, you write into some kind of output, which is also known as the exporter. We write all the trace data onto a Sherlock IO ingress endpoint. So if you really look at OpenTelemetry as a standard, it really talks about just trace collection and its format. The collector actually gives a well-defined mechanism to collect the traces, but how these traces are stored in the backend, what kind of features are made available on top of it, what is the experience that is there for the users is really up to us. And this is where most of the vendors who is within the tracing domain do their differentiation in terms of like they offer different features. So once the data is available on Ingress, we actually write it onto a backend storage of choice. Right now, we are writing the entire of this data onto ClickHouse backend. So once your data is available on the backend, how do you actually make this data more consumable for your users? So Grafana, as Amber pointed out a little earlier, that is like a one-stop solution for us for all our visualization needs, be it metrics, logs, or events. So it was clear from the onset that our experience needs to be on Grafana. So we looked at what's already out there. We saw that there's a Agar data source plugin for Grafana, which is useful for doing a point lookup for a particular trace ID. So what we ended up doing is we leveraged the same Agar data source plugin, we customized it and gave it a curated drill down experience to find traces. So if you just look at on this image, you can actually see, you can select an application, and from this application, you can select an operation, you can add as the tags as a key value pair as you need. You can add duration thresholds, and it will show up the traces in this particular view. The good thing with a newer version of Grafana 8 is this experience is already available, so you don't really have to build it. Essentially, what you need to do is to port your Agar query APIs. Now, it's also important to remember that not all the features or constructs of OpenTelemetry is really available for consumption through visualization. So we only use the ones that we really need, which can be depicted to the user on Grafana. The others we have either chose to ignore or do it at a later stage. So when you looked at different options for the backend, we had few choices. Before we just decided on ClickHouse, we did quite a bit of benchmarking on different storage options, which included Cassandra, TIDB, ClickHouse, and TempoDB. ClickHouse was very impressive when it comes to when it came to its ingestion throughput. Also, some of us were actually quite comfortable with ClickHouse, so there was always a bias towards ClickHouse. Cassandra also seemed pretty good. We were very excited about using Grafana Tempo, and we did explore it quite a bit. Unfortunately, right now, what you can do with that particular database is that you can only do a pointer trace ID lookup. Now, this database was actually created with tracing in mind. So it's like a first-class citizen for tracing database, if you can say that way. So we use few criteria while we evaluated the storage. One is, of course, it should be able to support high ingestion volumes, especially your traffic patterns can be quite sporadic. You might have a surge of trace data come in, so you should be able to accept all the data. Can support Eager query API patterns because we want to visualize that on Grafana. We also wanted to have the point trace ID lookups for a particular interval, just like what Tempo was providing us to. So from the benchmarking stand of view, what we did is we used a synthetic load generator. We profiled our processors on the OTEL collector, also on the ingress and egress. And based on the numbers, we decided with the right sizing of our infrastructure and how much we need, like if there is a certain volume of traffic, how much nodes we need to add on to be able to scale, or whether we need to separate out into different clusters. We were quite clear from the onset that alerting will be based on time series or metric data and not really from the trace data, which helps us in terms of setting up the SLA in terms of the query from trace data source. So why ClickHouse? One, open source and works very well with structured data. We have seen with other use cases that ClickHouse has worked well with things like OLAP. So we were comfortable using ClickHouse for high ingestion use cases, and our benchmarking also validated that. The storage footprint is significantly lower. It gives you a lot more flexibility. You can use custom codecs like ZSTD and so forth, which is great. It has Kubernetes operator support, which was which worked out quite well for us because most of our deployments are, in fact, all of our deployments are on Kubernetes today. Since we are a monitoring team, we always like to be aware of all the telemetry around our system. So we wanted to have extensive infrastructure monitoring place, which ClickHouse already did. And we had the inherent advantage that we had good in-house ClickHouse experience. So some of the observations, and these are observations that we have done on our infrastructure, and could vary depending on where you do. So I would actually encourage folks before like adopting a data store, do your own benchmarking on the infrastructure and then come up with your numbers, and not really depend on like different blog and posts there. They can be an indicator, but you still need to do benchmarking at your end. On the ingestion side, what we did see is that we were able to do around 350K spans per second with 4 CPU and 16 GB of memory. Some of them and our ingestion layer is in Golang, so we were spending quite a bit of cycles on garbage collection, and we actually over a period of time we actually reduced that footprint of garbage collection. Overall, when we did our exercise, we had a 3 KB of span size, around 20 billion rows, which on the storage came down to a compressed storage of around 300 GB, and average attribute length was around 20. On the egress side, when we were doing benchmarking, we actually essentially explored 4 different types of read operations. One is getting different services and operations, getting different spans for a service and ID, get by ID, and search by attributes. We were able to get good throughput the first 3. It is basically limited by the number of connections that you can have. You can always increase that as well. But search by attributes was the slowest because of the kind of schema that we use to represent it. We use arrays there. And that's the model that we need to use if we want to support things like tags. So yeah, moving on, talking about our deployment. Now, typically a single ClickHouse cluster is spread across different regions, or also you can refer to as different Kubernetes clusters. And within a region, you can have shards in different namespaces. Now, each namespace may be mutually exclusive in its usage of hardware, network, and so forth to keep isolation. And we use Kubernetes Federation for multi-region ClickHouse deployment. And we rely on 2 custom resource objects that we have created. It is referred to as the FCHI and FCHC that you can see on the green box here. Essentially, what those objects represent is that the FCHI is the collection of all the ClickHouse clusters that you have on your infrastructure. And the FCHC is talks about the individual configurations that is available on the cluster and where exactly it is available on. So what you essentially do is you create an object there, the FCSC object there, and it will create a remote servers.xml. Essentially, that's what it creates. And it will use that particular, it exactly knows where it needs to spawn your ClickHouse shards. So it will go to individual ClickHouse operators running in local Kubernetes namespaces within each region, and creates the ClickHouse installation object. Now your open source ClickHouse operator, which Altinity team has created, and we leverage that heavily, looks upon this particular instance of the object and then creates that particular shard. As the shard is, as the cluster is prepared, prepped up, the status is collected at the FCHC level, and that's how we know whether the cluster is ready for use or not. This typically would take us with maybe a minute or a little more than a minute to have the entire cluster ready. On top of this, we have also created some intelligence on how to do schema propagation in terms of how you can do prep up of tables and so forth. But just for the simplicity of talk, we'll not talk about some of those details. So continuing on the deployment, now you have your ClickHouse clusters. Now, how is your ingestion and egress layers aware of your cluster, right? That's important. So for that, what we essentially did, we wrote a small thin layer ClickHouse discovery module that you can see in green box and embedded within all of our components, which uses tracing data. Now this module is essentially, it uses just a simple kube informers to be receive any changes to the pods where the shards are provisioned and update its status accordingly. So the ingestion layer would essentially say that I want to write this application somewhere, and the discovery module will say, oh, you need to write to this cluster, and here take this handle and go ahead and write. Similarly for egress, it would be as simple as that. So we kept it very agnostic, and different components can just use this thin layer, and it has worked out very well for us. So if you really look at the internals of how this module library works, is that it creates a logical cluster overview, and it just uses that overview to get valid handles or get proper handles to write or read data from your ClickHouse cluster. So let's talk about the pipeline, right? We had certain decisions to be made when we looked at the pipeline. One is, I said we do use open telemetry collector. Now, where do we deploy that? So we deploy that on every Kubernetes cluster. And when we deploy that, we had a couple of options, right? Either you can have it running as part of a sidecar along with the application, or you can run it as a daemon set on the host, or you can host it as a centralized service. We decided to do the last option, the hosting as a centralized service, for reasons like resource fragmentation and to be insulated from issues like noisy neighbor problems and so forth. So applications would directly write data onto the OTEL service collector. But if you really look at the libraries that the applications use to write the data, they are written in a way that it will drop traces on the floor in case your endpoint is not available or is down or having some performance issues. So it will not really affect your the application itself, right? And which is good. So you don't want the application to be really affected by embedding a trace library or tracing library. So that's how all these libraries are designed, which is great. So your collector receives your data on the edge. We will scrub the data. We have custom processors. So scrubbing would mean that we remove any kind of sensitive PI data. And then we also would apply policies of rate limiting or any kind of custom sampling that we needed to apply. We also decorate those spans. Since we are running, these applications are writing to the local the open telemetry service collector, we can decorate the spans with more metadata, such as like pod information, your cluster application information, any labels that were available as part of the application deployment is available for us to add as a metadata on the span, which can give more meaning to the tracing data without the application owners needing to do needing to instrument it that way, right? So you get all this data on the ingestion collector, you write it onto the storage. On the storage, we have the query APIs exposed. You can have it consumed from Grafana, Agar, and we have our own internal cloud platform where we do embed this Grafana as iframes, and we can use the same platform to give the visualization experience as well. One interesting thing that we have done is that as you get the data on your ingress collector, we look at the events that are associated with a span. Now in OpenTelemetry, you can associate logs or events with a span. Now that data, we write it separately onto our generic logging pipeline as well. So, and this can be very verbose, right? And you can have any kind of text data there. And users can essentially now search for those logs on our logging console. And you also have trace ID embedded in it. So you can come back to a trace view, which that experience that I'll show in subsequent slides. But this is something that we have done and quite useful for our developers here. So we have multiple tables, but at the core of it, we use three top. These are three top tables that we use. One is a traces table, which allows you to fetch traces for a given service and op. It uses a replicated merge tree as engine. We have a traces SVC table, which will allow you to find all the associated service for a given trace. We use replicator replacing merge tree, which is very good when you want to really compress the records and reduce even the storage footprint. Similar engine, we use it for the SVC op, where essentially that table is used for looking up service to operation lookups, right? At its most simplified form, a table looks like this. You have a traces table with different attributes. We have other attributes that has its own dedicated columns. I have not put it here just for the simplicity reason. You will see most of the concepts from OpenTelemetry is available here. One thing that we had done is that we wanted to make sure that we can represent type of data, because you can have different kinds of types like bool or int for your attributes. So that is also represented in an array as an array. We can always mark them with low cardinality and have custom codecs, but at the crux of it, this is what at the top level the traces table look like. Here I was also showing the footprint. Now we are getting good compression with ClickHouse. If you use some other codecs, you'll get even more. We were at least seeing like 1:10 in terms of compression, which is great. If you compare something like with Elastic, it is actually so much better when it comes to the storage footprint, especially if you are using like SSD storage, right, which is expensive. So we use that today. At some point, we might move to some kind of block storage, but right now, storage cost is something that we are very sensitive to. So you have all this trace data collected. What else can you do with it, right? Other than just navigating with traces, doing point lookups and so forth. Right? You can derive a lot of useful metrics. Now these metrics are also known as red metrics. Many people talk about this, but essentially it stands for request, errors, and duration. So once you have all the traces data, you can essentially compute the number of requests that you got on every operation within your service. Where are the different errors that you have seen within a service? You can also derive things around duration, like what is the 99th quantile of a particular operation within the service. And you can also do more, right? You can add things around HTTP status, saying that, okay, give me a layout of how different how my HTTP status distribution looks for my service. That can give me insight about what kind of errors I'm seeing and how much is my error to success ratio and so forth, right? So we are exposing these from our ClickHouse data. So there is a metrics generator which looks at the trace data and generates these as events and writes it back to our platform. An interesting thing about this particular visualization that you see is that it is also coming from ClickHouse, not from Prometheus and so forth. So we have implemented a low-key equivalent on top of our events data, and all the visualization that you are seeing here is actually coming from there. Now sampling. Now this is a topic of high context, like people have strong opinions about how you want to do sampling. So basically sampling means that you're taking a decision on whether you want to export a span or not. And you have different ways to do it. We use tail-based sampling because what we wanted to ensure is that we can have 100% accuracy with respect to our red metrics. So if you do sampling, you might lose visibility there. So we do that. And we do sampling based on different attributes like latency, errors, and HTTP status code. So this is where we are with our sampling story. There is much more that we can do in this space. But before we implement, what we have essentially decided is to roll this initial version out, get the feedback from our customers and see whether it works and what really would our customers like in terms of getting the sampling enabled. We already have some feedback, which I can share it towards the end. So Amber initially touched upon this in his initial slides, that traces is something that can be used to unify different telemetry signals. So we wanted to make sure that that experience is available for our developers. So as I said before, you can embed your, you can write your trace events into our logging platform, and it will have something like a trace ID embedded with it. You click on it and then it will take you to a Sherlock IO tracing console. Now this we have just piggybacked on what Grafana is providing, but what we have essentially done is to make sure that that particular data is available on our logging platform, and there is a context in terms of switching from the log view to your trace view seamlessly. The other way around is also possible. And the reason why it is possible, if you remember that I initially talked about the K8 processor, wherein you add metadata like pod, application, and so forth. So you can have now consistency between all your telemetry signals that will allow you to actually jump much more easily from one signal to another, as long as you have consistency in your metadata, right? And you can similarly do something from metrics to traces. Now this is something we haven't opened it up yet, like we don't have it in platform, but I'm personally very excited about this. So the way we would do it is that once our metrics can actually have a trace ID information embedded in it, you can look up something called exemplars, which talks about this, and we want to leverage that going forward. We haven't done it so far, but you can embed an trace ID within your time series data and jump from a metric to a trace. So when you plot your time series data, as you're plotting on the left side of the panel here, you would see a small dot here that would be a trace ID associated with that particular time series. So here you can see the 95th percentile is somewhere here, but you saw a trace ID which is above the threshold and is certainly of interest to the user. So he would try to see what kind of trace actually contributed to that kind of high latency, right? So we are actually quite early in our journey. We are like a couple of engineers who work throughout the year to actually get a version of the tracing platform going. We have some help from our SRE folks who have been helping on the integration side. So there were many challenges that we saw in terms of when it comes to adopting distributed tracing. So what we have learned is that it is really hard to justify a need for an additional telemetry signal like traces, especially if you ask your customer to do instrumentation. And not just that, say if you have like 4 applications maintained by 4 different owners and you want to trace all the entire flow, then you would need to have tracing enabled on all of them so that you can have the entire request propagation working nicely. And that can be hard as well. What can we do to make it things simpler? So what we thought is that, okay, within eBay, and I'm certain within many other organizations, you use some kind of framework. So that framework would be like an interceptor for your outgoing HTTP calls, or some kind of you'll have some DAL calls or whatnot. So you can embed your integration or the tracing integration endpoints within your framework directly, and thereby making the developers agnostic of the tracing integration. If they need more rich trace data, they can always instrument in their application directly. But that's like if they want to do that, they do it. Else they always do get the tracing for free. And not just that, once they have it enabled like that, the downstream, the application will also receive it, right? There are other challenges also. If you have something like a message bus in between, how do you make sure that you can have the propagation of trace data? There is, the standard also talks about it. We are implementing an early version that will enable that. Another one that I briefly touched upon is on the coverage. How can you increase the coverage? So we are on Kubernetes. We are now planning to use service mesh for almost all our deployments. So service mesh is a nice way wherein it can also emit traces. So we would integrate directly into the service mesh, intercept those traces and collect onto a platform. Thereby, you will get visibility into any incoming and outgoing trace from your application, which is great. So you have at least visibility on the transport level. And additionally, if the application wants to instrument, they can do it within their code. Sampling is another one. We've been collecting feedback. Some of the things that we are looking into, like if the customer says that I want to save a particular trace for a longer period of time, can I do that? Can I retain my data for a longer retention? Can I do custom sampling? Because say an issue is happening in production on a particular host. Now they say that, okay, I want all the traces from this host to be available for 2 days. So because it happens very rarely, and I just want to catch that even whenever it happens. So we are looking at ways to actually enable it, and there is certain challenge when it comes to enabling this because of the storage cost and even the infrastructure footprint in general. So we are looking at these problems in general and looking at the way to best address them. Yeah, so I think with that, I have come to the end of my slides. I handing it back to you, Amber.
Thank you, Sudeep. So just want to close with the plug. We are hiring across all of our engineering teams, across multiple levels, all the way from recent college graduates to experienced engineers in different departments, product management included. You can explore the opportunities at career.ebayinc.com, and please feel free to reach out to Sudeep or I if there's any position that interests you. With that, thank you everyone for attending. We're open for questions.
Thank you.
All right. I think the only question that we had was already answered. That was regarding, whether or not you guys were using the open source operator. So let me ask, so when you, in writing that, was there a reason why you didn't go with the open source ClickHouse operator for managing clusters? Was there something?
Oh, we did. So as I said, maybe John, I did talk about, we do use it. So the only thing is that it doesn't allow you to have cross-region deployments. So we had to build something on top of it to allow us to actually spawn clusters across regions.
Oh, cool. Okay. So, and you guys are still using Zookeeper and the like for the cluster for all the clusters. Okay, just curious.
Yep.
Yeah, that's actually a good question. So we probably over-engineered it. We wrote our own Zookeeper custom operator, which can create Zookeeper instances across regions as well.
Gentlemen, thank you both very, very much for your presentation. That was some thick, awesome stuff, and I appreciate all of your effort in going into that, all the work you guys have done. It sounds really exciting.
Awesome. Thanks, you so
John.
much.
Wonderful being here. Thank you, everyone.